Hello, I'm Chris Athanas. I'm a KMP developer. Tech support's coming out Tuesday for that. Hopefully, this time they'll come out for reals. Today, I'm continuing the series called How to Program. Let me get my stuff up here. How to Program from the ground up. And we're getting into some of the nitty gritty stuff. Getting into the data structures. The big idea of data structures is it's easier for humans to deal with names of structures that we all just give a name thing. We love to name stuff, right? That represents how we think about laying data out in memory. And it's easier than just a hex code address and trying to read the code and figure out what the heck's going on or comment somewhere. So we just gave these names to things, these ways of dealing with sections of memory. So how something is arranged is 80 IQ points to the problem. So there's 100 IQ. Out of 100 IQ, if you can arrange it, if you can arrange the problem in a certain way, that's 80 IQ. So so we've given names to these things. The real basic starter one is numbers. Having those bits actually represent numbers. But let's do a quick breakdown of these kinds of things. Matt, you do need to know a tiny bit of math to do computer stuff, which is really more just how things get organized. I think the term computer science is a little bit off. It's more like organizational science. And the guy that coined the term computer science was referring to this organizational process, how things can be organized. Because after you get above the computer engineering of the bits and bytes and the wires and the diodes and stuff, it then becomes this organizational stuff. How do you organize these things to do something useful? So here we go.
People often say you don't need to know any math to program a computer, and that's truthy. However, any sufficiently advanced technology is indistinguishable from magic. But magic isn't real. Math explains it all. Developers often avoid learning math because it looks scary, but it actually makes complicated magic.
These are just like, here's a loop. Here's like adding up little pieces, adding up an array of little values. Once I figured out that these are just algorithms, like very simple algorithms for doing these mathematics, it was like, oh, okay, that's how they're mapping the math, this particular type of math called discrete mathematics, into computers.
Like computer graphics and neural networks easier to understand. And not just that, but it unlocks the secrets of the entire physical universe. There's a few abstract math concepts for programmers that you just can't ignore, and understanding them will make you think more like a true engineer. I'm no math genius, in fact I'm the opposite, which makes me uniquely qualified to teach 10 essential math concepts using memes and other visual aids that almost anybody can understand. The first person who survives until the end and cracks the code will win this one-of-a-kind Balenciaga Fireship hoodie. Let's jump right into topic number 1, Boolean algebra, which is used almost every time you write code. A Boolean is a binary variable that can have two possible values, true or false. Now there are 3 operators that you can use to work with them, and, or, and not, or
that builds it all.
For conjunction, disjunction, and negation.
Never everybody uses that.
If you want to be fancy. Imagine you're trying to get a girlfriend. We can use the Boolean variables of rich and handsome to describe you. If you're both rich and handsome, you'll definitely get a girlfriend. But if you're not rich and not handsome, you'll have to pay for an OnlyFans girlfriend. If you're rich or handsome, you can still get a girlfriend, but your selection is more limited. We can represent this logic in code with things like if statements, but we can also do it visually with Venn diagrams like you've been doing since grade school. And you can also create truth tables like this one here, which comes in handy in zombie apocalypse type situations. But that brings us to concept 2, numeral systems like base 2. Throughout history, humans have come up with all kinds of clever ways to count things, but almost all of them use base 10 like the 10 fingers on your hands. Like in the number 423, the 4 is in the hundreds place, which represents 4 times 100. The 2 is in the tens place, or 2 times 10. Then the final number is multiplied by 1. But computers work off of a base 2 numeral system. In base 2, things work the exact same way, but because we only have 2 symbols to work with, each place is multiplied by 2, like 2, 4, 8, 16, 32, 64, 128, and so on. Now that you understand that, you also understand how other bases work, like base 16 or hexadecimal, which uses the digits 0 through 9 along with A through F, and is commonly used to represent binary values in a more concise way, because each hexadecimal digit can translate into 4 bits. And you also have base 64, which introduces even more letters and symbols to encode binary values, allowing developers to represent binary data like an image as a string of text.
It's the same stuff over and over. What about base 128? Well, if you had two more bits there, you could probably do it. If you're doing 2 bytes at a time, you go, we're doing base 120, 256, base 256. Ooh.
While computers use base 2 under the hood, they still need to represent base 10 numbers for humans, and the most common way to do that is with floating point numbers. Go ahead and execute 0.1 plus 0.2 in your favorite programming language. The result should be 0.300000004.
Right, we'll get into why that is, and this is something to be aware of. In computers, when they're doing floating point numbers like this, anything with a dot after it, that's called floating point. There's a reason why they call it floating point, which we'll get into, is because it's always approximate. You can say one's greater than the other, one's lower than the other, or you can compare an integer to one's greater than or lower than, but you should never say equal. Can never do equal, double precision, whatever, anything that's a floating point value that you can never determine whether they're equal. And the reason why is because it's taking the fraction. So when it's down here, it's so you have think of an inch. So you have an inch is, say this is an inch, and then say okay, and then what's a tenth of an inch is down here. Okay, that's this place right here. So how many of those? And then you have a hundredth of an inch, which is this place, and then 1/1000th of an inch, which is this place, and 1/10,000th of an inch. So by the time you get down here, I mean this number at this particular scale of 1 inch means nothing. And this is where we get into what these are actually representing. Because if you're just doing an inch, this means 0. It means it's less. You could ignore it. Anything past really past here, for our scale of human scale levels. But if you're doing planetary scale levels, or you're going across universe or the galaxy galaxy scale levels, this becomes a big deal. This is the size of a sun. So it's really what scale are you using at? And this is where knowing the precision, how many digits of precision, why, and with how that's useful. Becomes useful in engineering operations, or if you're using large scale things where you're starting to use floating point values. That's why you have to be very careful about when you use them and why. Sticking to integers is probably for most business cases. Even if you have to somehow divide them by 100 to get to dollars, they actually store things as pennies because of this problem, the round off problem. So it's good to know that why this is a major limitation in computers, and it's crazy that we still have to deal with it. But it's just how we count in binary. Now there are systems that you can use that will be exact, and you can do it. But this IEEE standard, no. And then just in general, if you're going to be comparing two floating point numbers, why are you trying to compare this down here? Why are you doing that? In fact, if this becomes important, then you have to ask, why are you using a scale that comes where this digit becomes important?
How could a computer make such a silly mistake? Well, in science, numbers can get very big when talking about space and very small when talking about things like atoms. We don't...
Right, what I just said. So if you we're going to get into it right here, but you can actually have these little visualizers, which will show you what each digit represents and why this thing, you'll never, here it is, this thing here. This sets it up. So you can take a digit, and type it in the digit here to get the digit out you want. And then you can go to this toy and set this up, and it'll show you the equation that the math that it's going through to with all these equations here, which is how it's getting this actual value of this final result here. And it's just doing a little loop here. So that's 0 to 51 digits of all this stuff. So that's how they get that going. Let's keep going with this.
Write these numbers out completely and instead use
And of course, I'll put all the links to that stuff in the doodly-doo.
Scientific notation, where an exponent raises it to an approximate value, making the number appear far more concise. Computers use a similar approach with floating point numbers because they only have a limited amount of space, either 32 bits for single precision or 64 for double precision, which is the default in languages like Python and JavaScript. It's called a floating point because there's no fixed number of digits before or after the decimal point, allowing developers to make a trade-off between range and precision. Some numbers like 0.01 can't be represented perfectly as a binary floating point, which is the reason we get those tiny rounding errors. Now that you know how numbers work, we can start talking about logarithmic functions, which you might remember from algebra class. To understand them, think of an actual log. The log starts at 16 feet, then we saw it in half over and over again until we reach a length of 2. Notice how when we try to draw a line through it, it's not perfectly straight, but rather it curves gradually. In computer science, this is how many algorithms work, like binary search. What's interesting though is that if we know how many times we cut the log,
it's funny he's using the log thing. because it has nothing to do with that. But it's cool that he's using the log metaphor so people remember. That is very actually quite awesome.
Computer science, this is how many algorithms work, like binary search. What's interesting though is that if we know how many times we cut the log, we can raise 2 to the power of that value, in this case 4, to get the original length of the log. That's called exponentiation, and logarithm is the exact opposite. Imagine we don't know the exponent, we only know the original length, and want to figure out how many times we'd have to cut the log to get a length of 2. We could calculate that with a base 2 log on the original length, returning a value of 4. When it's
Yeah, it's really important to know those two. I mean, I'm not super important, but it's like it's how we multiply and divide in computers because everything's times 2 divided by 2. Always 2, 2, 2, 2, 2, 2, 2.
base 2, it's called a binary logarithm. However, in math, it's more common to use base 10, which is called the common logarithm. That'll come in handy, but now let's shift gears to set theory. A set is just an unordered collection of unique values. The best example is a relational database where each table is a set of unique rows. These tables can be joined together in a variety of different ways based on set theory. Like to select records that match on both tables, you do an inner join, which is called an intersection in set theory. Or to grab all matching records from both tables, you do a full outer join, which is a union in set theory. When doing left and right joins, these concepts are combined, like by combining an intersection with the difference between the two sets. Now, one thing that's important.
Okay, he just went off in the weeds a little bit there. All he's talking about there is like database tables when you're doing a search and you're trying to combine it. Like say you have a name of students and the name of the classes, and they have there's a student ID and there's a class ID, like matching those up. Okay, so if you have this class, who are all the students in that class? And go, and then you have like who for this student, what classes does he have? And then, that's all it is. So there's just different ways of doing that, and it comes with that Boolean logic. It's like, this is so silly. Is he making these really crazy Venn diagrams? It's just you're searching. Okay, if I have two tables, I'm going to do an intersection between this student and the classes the students in. Ooh, they overcomplicate the shit out of it.
Important to notice at this point, concepts are combined, like by combining an intersection with the difference between the two sets. Now, one thing that's important to notice at this point is that we're talking about structures that have a finite number of elements, which falls under the umbrella of discrete math, as opposed to continuous math, like geometry and calculus, that deal with real numbers and approximate.
Right, all this stuff for computers over here. We are simulating this stuff over here. And we never get over here. This is all like all the equations and stuff. Then we just discretize this. Means little chunks. Discrete means little tiny pieces. Because that's all we can have with computers. All we get is pixels. We only get a cell that has a 1 and a 0, or a bunch of cells that represents another cell. We can't just do the whole continuous thing. We had computers that predated the digital stuff, but every single machine, the CAM that determined that curve or whatever we were trying to work with, had to be custom ground, custom made for each calculation. No, that's not scalable.
Approximations. And that brings us to our next discrete topic, combinatorics. Simply put, this is all about counting things, especially when combining sets into combinations or permutations. Like if you have an app like Tinder, you might need to count all the possible combinations of matches as part of a more complex algorithm that figures out what to show the end user. Or maybe you're building a globally distributed database and need to figure out how many database partitions you'll need around the world.
I love that starting. It's sharding, which means like in a crystal or a piece of glass, when you crack it, all the shards go in different directions. So you have a full plate of glass, but if you smack it, it breaks into 1,000 little pieces. It's still one plate of glass, but now it's all in different little pieces. Those little pieces are called shards, and that's what they're talking about here. Is they want to split the database geographically according to some function. It says, well, San Francisco, if you're a San Francisco person, you should be in the San Francisco database. If you're in LA, you should be in the LA database. If you're in the, if you're it's like a dating app, right? And if you're down San Juan Capistrano, you should be down there. And if you're in New York City, you should be in the database in New York City. So that's what they're talking about here. This hash function. It says, given the state you're in or city you're in, go use this particular database or that particular database. That's all that is. That's it.
World. Ultimately,
and then starting, of course, is pooping your pants.
it's all about understanding how patterns can emerge. What you're looking at here is the formula for the Fibonacci sequence. A great exercise is to write a function that generates it. Congrats, bro. You just did combinatorics and unlock the secrets of the universe.
Right. So this is also called a recursive function here. And, there's always a piece, a little smaller piece, a little smaller piece, a little smaller piece. And that's the idea.
Engineers at Google use the same kind of logic to render tiles on tools like Google Maps, and the gods use this pattern all over the place in nature. Combinatorics is closely related to graph theory. A graph has two basic parts.
I hate that word theory. I wish they would call it, because they're bringing this stuff from math, and so it's just like this graph use. How's that? How do we use this idea of one thing that's connected to another thing? Graphs. Ooh, I mean, like network. Are you calling it like a network? So one thing is connected to another thing. It could be connected to more than one thing. You mean a network? Graph theory. Stop. It's okay. How can we connect? I have Lincoln Log Legos. How can we connect these all together? Come on now.
Nodes or vertices and edges that connect them together. Like a person might be a node and an edge might be a relationship that
Okay, why don't you just say okay, node is fine, but how much is connection? Why do we have to call it edge? That's confusing. I know because you have 3 of them you can create a shape. This is all coming from the math people.
connects them together, like you love your mom and your mom loves you back. This is an undirected graph because the relationship goes both ways. However, you might also love your OnlyFans girlfriend, but this would be a directed graph.
Okay, one direction. So this last one here was because, where is it here? Go back here, you little bastard. Come here. This one, this undirected means it's just connected, right? Undirected, connected. I hate why, I don't know why he had to do this arrow like this, because it just means they're connected. Okay, I guess because he's showing that it's undirected because it's one arrow. Okay. So directed means
graph
one
because
direction.
The relationship goes both ways. However, you might also love your OnlyFans girlfriend, but this would be a directed graph because that relationship only goes one way. Edges can also be weighted, meaning one relationship is more important than the other.
Okay, it's like a distance, right? So instead of drawing out all the whole thing, you just put a number here. This is 99 miles away. This is 7 miles away. This one has another different constraint on it. Like, oh, this one costs $4 to go across the bridge, but I only have $2. Well, you have to go this far, and it's going to cost you, it's much more time. Blah 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 blah. So they have these fancy terms on stuff that's like, okay, I already know that. I already know that if I go this route to work, it's going to take me 10 minutes. But if I go around this way, it's going to take me 15. But it's going to take me longer. But I'm going to miss that traffic. Okay.
Back to itself, it's called cyclic. Otherwise, it's known as acyclic. As a programmer, you'll often
cyclic. Okay, so if it goes in a circle, it's cyclic. And if it doesn't go in a circle, it's oh, come on, stop. This stuff is so silly.
You need to build graphs from the ground.
People make a really, really, really big deal. Like this is like some amazing, profound stuff. It's like common sense, guys. Come on.
Up, but more importantly, know how to traverse them, like when using Dijkstra's algorithm to find the most efficient way to navigate through traffic. But before you start writing graph traversal algorithms, you should
right. So these things are like you're supposed to like regurgitate these things
and
find
the
most
efficient way to navigate through traffic.
Okay, it's important to know how it works, right? This clever PhD level stuff this guy had to figure out for his paper on how to do this, how to travel through a network like this, right? Graph with nodes and edges, like how to go and weighted and how to travel through it the most efficient way, or at least one way. And we're supposed to regurgitate this and this leak code stuff. Well, that's over. You do have to know how it works. It is useful to write it out and play with it. And so it is very useful because it'll train your mind. It's like, oh, I see, you can do this kind of stuff. But how often have I tried to like implement my own version of this? No, I just use his. If I need to go between 2 points, I'm not going to write my own graph traversal function. I'm going to say, here's A, here's B. Tell me the nodes I need to visit. Thank you.
In graph traversal algorithms, you should know a little bit about complexity theory, which can tell us in theory how much time and memory an algorithm should use. We use big O notation.
Oh, this is useful. We'll touch on this a little bit later.
To express complexity, and when talking about time, the input represents the number of steps it will take to complete a task. Like if we read a single element from an array.
Right, so the simple idea is, how long is this thing going to take to run? Because every time step takes time, and time is money. Okay, blah, blah, time is money. And like, given this algorithm, the way it's set up, you can look at it and go, oh, it's just doing a simple lookup. So that's an O of 1. If there's a bunch of things it has to scan through, like a list of items, like if there's just not one item, there's like a bunch. Okay, you have to look at each one. You're just not going to go guess. I mean, that may be one way of doing it. You could get lucky, but worst case scenario, you're going to look at them all before you find the end result. So that's the worst case. We're talking about the worst case scenario. How in the worst case, how long is this going to take if I have to do this whole thing?
Array that would give us O of 1, or constant time, which is extremely fast and simple.
Constant time. How much is O of 1? It's a simple lookup. Okay.
If we need to loop over an array, that would give us O of n, where n is the length of the array. But if for each iteration in that loop, we loop over the same array again, that would give us O of n squared.
Ooh, so 2 loops. So I'm doing this one the same time. So this many times I'm going to have to do this one that many times again. ooh, it's so complicated and squared.
Which would be far less efficient. However, more sophisticated algorithms like binary search cut the search area in half after each iteration, providing us with logarithmic time. Understanding how to measure complexity.
All right, so logarithmic times just means divide by 2.
Search cut
That's
the search
it.
area in half after each
Divide by
iteration,
2.
providing us with logarithmic time.
Every item you get, it gets half as long as it goes along.
Understanding how to measure complexity is essential for technical interviews and is just a good thing to think about in general. But now let's move away from
Agreed. There is kind of a barrier. You do have to know what those little things mean and why that is that way. But it's not overcomplicated. Don't overcomplicate it. Don't overcomplicate it. It is a barrier, but people do make a big deal about it. It is talked about. It is a good way to refer to things. If you see something implemented with a triple loop, you know that thing ain't going to end anytime soon. Like for small numbers, it's fine. 10, 20 elements. But for like 100 elements, if you're doing 3 loops, even do 4 loops, the end of time kind of level stuff.
Greek math and talk about statistics, which is crucial if you want to do anything with artificial intelligence, because machine learning is kind of just a fancy way of doing statistics. Like when you type into ChatGPT, it generates a response based on the probability that it fits the prompt provided by the user.
Right. It's just this thing. It's just
like when you type into
ChatGPT. Statistics. It's just determining what likely in your context of the thing you've already done that it's already seen and been trained on. How likely is it going to be this thing? I don't know. Is it this one? Is it this one? This is the hallucinations.
It generates a response based on the probability that it fits the prompt provided by the user. At the very least, you should understand mean, median, and mode, and how standard deviation indicates how close values in a set are correlated to the mean.
Okay, yeah.
Median, mode, and how standard deviation.
Right here. So that means that most people are going to be right here in the middle of the hump, right? 68% of the people of any population of whatever you're sampling, 68% of the time is going to be here. Then another 13% of the time, or 27%, whatever, 28%. It's going to be half the group is going to be the worst, and then half the other group right over here is going to be the best. This is called a standard deviation. One standard deviation. This little thing right here is this part of the hump is this symbol, one of these, and then 2 of these over here. And then way out here, 2.1% is the third deviation, third standard. So a tiny number of people, 4%, 2% are stuck. These are going to cause a lot of problems. And these are going to be your superstars. Everyone's going to be like, you could just be like them. It's like, no, there's like going to be 2% of those anyway. And then over here are your mass murderers, serial killers, psychopaths. And here's your saints that are actually preventing World War III.
Indicates how close values in a set are correlated to the mean. There's a ton to learn beyond that, but what I found especially useful is the difference between linear regression and logistic regression. In a linear regression, the goal is to predict a continuous value, like the amount of money you'll lose after buying a stock. The relationship between the input and output variable is linear, and the idea is to find a line that best fits the dataset. However, logistic regression is used for an entirely different set of problems, like classification. Maybe an app that predicts if an image is a hot dog or not a hot dog.
Yeah. Whew, geez, this is a tough one for me. This one, obviously hot dog. But this one, is the dog actually hot here? Is it panting? No, I thought his tongue was out for a second, but it's just a blue dot. Indeterminate. I'm in this range here. My detector is a little off.
In this case, the relationship is not linear, but rather a sigmoid function, which might predict the probability.
Sigmoid. Yeah, so when you see these technology adoption curves and it's hitting this point right here, and they're like, this is going to go on forever. No, it's going to peter off here. So when it hits that peak, mass adoption, like right here, oh my God, this is the best thing ever. And then, not so much. This is kind of max them out. I've already had 25 Cokes a day.
That a Boolean variable is true or false. And that brings us to our final and most difficult topic, linear algebra, which comes into play in things like computer graphics and deep neural networks. To comprehend it, you'll need to understand 3 weird words. Scalar is a single numeric value. A vector.
Okay, so when you're multiplying something together, you're using a scalar. Each value is a scalar. This math stuff is so silly. It's okay. One value. All right, one value.
Vector is a list of numbers.
Oh, a list. Oh, okay. Wow. So like an array, like a list. We're going to call, so another word, vector. Okay, so the same stuff, just a series of numbers. Okay.
Like a one-dimensional array. And finally, a matrix is like...
Oh, wow, a matrix. We gotta call it a matrix. The math people coming in again, pooping all over the place, making up these weird words. Oh, you mean just like an array, like a grid? Okay. Stop, guys.
Like a grid or two-dimensional array that contains rows and columns of numeric values. What's cool is that vectors can represent points and directions in the 3D space.
Oh, you mean a vector can be a point? Oh, wow. So two values, an x and y on a grid. Wow, that's really breakthrough, guys.
While matrices can represent transformations that happen to these vectors.
Yeah, that's cool, right? So you're just multiplying each one of those XY coordinates by this thing to get a new XY coordinate. Oh, wow. Wow, matrix multiplication. It's so crazy hard. Stop, jeez.
When you move a player around,
it's good to know. It's good to know how this works.
Space, while matrices,
but don't make it all like, oh, it's so crazy hard. It's like one of the simplest stuff ever. All you're doing is multiply one number to another number to get a different coordinate, to get another number that represents this. This represents that. This one over here is over here. It's been translated and rotated and flipped. It's just mega. If it's positive, you make it negative. I mean, it's like, come on. They make such a big. People make such a big deal about this stuff. Honestly, that made it way more confusing for me. It's just multiplication and addition and subtraction. That's all it is. And they give it a name. So when you have a certain type of matrix that you multiply the numbers together in this particular clever way, it's called a transformation matrix, or a scale matrix, or a rotation matrix. Stop. It's just multiplication, clever ways. If you got into this, you would discover it anyway. It's not like it's the most amazing we discovered. No, it's okay. You would have figured it out. It would have become. You do it over and over. If you did it 50 times, 100 times, you go, there's a matrix. Oh, okay, you multiply the numbers. Oh, I can see you'd figure it out. It's nothing groundbreaking.
These can represent transformations that happen to these vectors. When you move a player around in a video game, the lighting and shadows in the graphics change magically. But it's not magic. It's linear algebra that's being distributed on your GPU. Imagine
it's just like you just showed you there, just multiplication. It's just multiplication, division, subtraction. That's all it is. Usually it's multiplication. That's all it is.
2D vector that's at point 2x, 3y. It represents a single point in an image. We can perform linear transformations here, like scaling, translation, rotation, shear, and so on. Let's imagine we now want to scale the point.
Just multiplying numbers to that matrix to get another number. Ooh.
To a value of 4x, 6y. We can represent the scaling factors in a matrix, then represent the point as a column vector. And now we can use matrix multiplication to scale the point to its target location. Operations like this are also essential in things like cryptography, such as RSA encryption.
Yes, it's used all over the place when you need to take a number, do something to it, and output it. Really? There's that's useful? Oh, okay. Got it, guy.
And are also essential in deep neural networks, which use vectors to represent features, then use matrix multiplication to propagate values between nodes in the network. The underlying math is surprisingly simple.
Yeah, it's because it's all the same stuff. These computers really don't do anything different than multiplying, adding, subtracting, yes or no, jump here, jump there. This is all clever human stuff. This is all human cleverness that discovers. So I'm doing this stuff over and over and over again and going, okay, let's just standardize this. And there's the standard. Well, it's not like, oh my God, it's amazing. It's just like, no, we can cleverly make things look like they're doing something, and we'll give it a neat title, a new name, but it's the same old stuff, just variations on the theme. And the good news is, this is all it is.
There is a massive amount of computing power to handle the staggering
so you can just use it how you want.
Amount of data required. As you can see now, math is actually not that complicated, and the more you study it, the more the computer will reveal its magic tricks. Thanks for watching, and I will see you in the next one.
All right, so we covered that. I'm at 22 minutes. I'm gonna go to the next episode. Give us a little break, a little breather. I need to calm down from my ranting.